In this video, I'm going to show you a method to test the difference between two standardized beta weights derived from the same multiple regression analysis. I'm going to say at the outset that a method of testing the difference between two standardized beta weights is not really well established, certainly not with asymptotic normal distribution theory. I can think of a robust way of doing it in a program like AMOS, which is more of a path analytic approach. I'm not going to show that here. Instead, I'm going to show you an approach that I think is actually probably on the conservative side. So if you find a significant effect with this approach, it probably definitely is statistically significant. And the approach that I'm using here is based on the article by Jeff Cumming in 2009, where he showed that confidence intervals can overlap by about 50%. And once they overlap less than 50%, usually it denotes a statistically significant difference between the 2-point estimates. And in the title, it mentions independent, which implies that the variables are unrelated. In the context of multiple regression, the variables are almost always interrelated. And as the interrelation increases, I would say that this test becomes progressively more conservative. So if you find an effect based on this method, I would say that probably statistically significant. At some point, someone will publish a method to test the difference between two standardized beta weights that may be more accurate and more powerful statistically than what I'm going to show you today. But in the absence of that, here's one method. So in this study, education and IQ were both found to be associated with positive standardized beta weights in terms of contributing to the regression equation predicting earnings. And the question is, can I say that education's standardized beta weight is statistically significantly larger than the IQ standardized beta weight? So 0.232 versus 0.174. Well, the method I describe in the textbook involves creating a high-low chart. And to do that, you need to set up your data in another data file. And over here, I've got the point estimates. The standardized beta weights are right here, 0.232 and 0.174. I grab those from this portion of the table in SPSS. And then I've got the lower bound estimates, LB, 0.09 and 0.031. That's where I got these values here, 0.09 and 0.031. And finally, the upper bound, 0.375 and 0.16, 0.375, 0.316. So I've got the point estimate for education with its upper bound and lower bound all in one row, and the point estimate for IQ with its upper and lower bound. Now next, you'll want to open up a syntax file and input that piece of syntax that I included in the textbook. Graph, high-low, simple, equal value, upper bound, lower bound, point estimate. These are the variable names. Make sure you don't have any other data files open, because this is going to reference the data file that's open. And if you want to make sure that it's the one that you want, which is this one, make sure this is the only data file that's open. Once you've done that, click Run. And SPSS will create a high-low chart with the point estimates and the upper and lower bounds associated with each variable. In this case here, variable 1 is education. That's that point estimate that was estimated for education, and this is the point estimate that was estimated for IQ. Now clearly, there is a huge amount of overlap between these confidence intervals. And I'll just clean that up a little bit. Alright, so that looks a bit better. And we can see that clearly there's a huge amount of overlap. In fact, the upper bound of IQ's standardized beta weight exceeds the point estimate of education's standardized beta weight. In order for it to be statistically significant, this upper bound can't go further than 50% of the confidence interval on the lower side for the other standardized beta weight. So it's obviously greatly exceeding the point at which I can declare statistically significance between these two standardized beta weights. So let's look at a data file where there is a statistically significant difference. And I just made these data up. So they're fictitious data. So let me just open that. Okay, so I've opened up the other data file that's going to produce a statistically significant difference. I'm just going to close the other data file, and I still have the syntax file that was used in the previous example. So I'm just going to run this again. I'll just clean this up. In this case here, the point estimates are exactly the same as the previous example. So 0.23, 0.232, and 0.174. It's just that the confidence intervals are much narrower. And this is what it produced in the graph. And you can see that that's probably less than half up the lower point And it's pretty plain to see that the upper bound of the lower point estimate does not exceed the halfway point of the lower bound confidence interval associated with the larger one. So I would say about half point is there, and because this is lower than the half point, I would declare these two standardized beta weights as statistically significantly different from each other. Now in the textbook I show you how to do the actual calculations in order to test it precisely. This is an eyeball view, and sometimes that's all you're going to have to do. I mean, clearly there's no difference between these two standardized beta weights, and in my opinion it's pretty clear that there is a difference between these two because this does not exceed the halfway point of the lower bound confidence interval. Again, this is an approximate test. I think it's probably a little bit conservative in the context of multiple regression because the independent variables are correlated with each other, and all other things equal, that should help enhance the statistical significance testing of the difference between the two beta weights. Again, until a more precise method is developed and implemented with software, this is probably the test I would use, except if I were using a program like AMOS, which I know a way to test that better with some syntax within AMOS. I'll probably show that in another video sometime in the future.